Hi, in this example, I'm going to be looking at or it's a collection of synthetic mixtures. So John Andrews at the University of Colorado and his team took several pure mineral samples and ground them up and mixed them in various proportions and prepared them properly for RockJock. Anyway, so we're going to load those up, and I'm going to show you one kind of strategy for doing the analysis. So these particular standards that we're going to be looking at have corundum, or the particular samples we're going to be looking at have a corundum standard spike. So we're going to leave everything as is here, but I'm going to check the multi-sample here because I want to load multiple files at once. Let's say load data. So all of the text files are in here in this folder. There are other files that do not have the .txt extension on them, so RockJockML is just going to ignore those, and it'll assume everything with the .txt file in that folder is just a text file with one column of intensity data. Okay, so it loaded them up. If I click on the pattern number here, you can see there are 16 different patterns that loaded up. So we're on number 1 here. Now all of these samples, like I said, have the same minerals, but they have different proportions of the different minerals. Actually, the first 4 are just replicates of the first mixture. The second 4 are replicates of the second mixture, and so on. So this 1B1, this is just the first replicate of the first mixture. Anyway, this is analogous to, say, if you were analyzing the mineralogy of sediments in a core that you collected. So you have sediments in the same area, but due to whatever different climatic factors and so on are going on, you might have different proportions of the same minerals in different layers. So that's a good reason to load them all at once and then try and get the same analysis working for all of them, and then just report the results for all the samples based on analyzing for the same minerals. Okay, so I'm looking at this one here, and the strategy I'm going to use here is to just go over to the Compare tab right here. So I'm going to click on that, and in here it has my pattern. So the blue is just the data. The red is the calculated pattern. And since we haven't chosen any standards to compare to, this it's just taking into account the internal standard, the corundum. So you can see which peaks belong to corundum in this. Anyway, down here on the bottom, we have 2 tables. This table is just an alphabetical list of the standards. So if I click on anything here, like this calcite right here, the pattern for calcite will show up on the bottom here. So you can see in the legend here, the calcite is the purple line. This yellow line is the difference pattern. So it's basically the blue pattern, so our data, and then subtracting out the calculated pattern. So it's what's left over after fitting whatever we've chosen so far. And so you can see right here that calcite is actually, you can see right here, there's a peak in the right place where the main calcite peak is, and everywhere else where calcite has a peak, it looks like there's something going on. So this is a good candidate. But right now I'm just going to click over to the side here and then re-click the calcite and deselect it. And show you this, what I'm going to do with this table over here. So this is the suggested table. And every time I update the analysis, this is going to update as well. And what it's going to do is take that difference pattern and it's going to calculate the correlation coefficient between that difference pattern and all the different minerals in the database. So it actually excludes amorphous materials, but if you have a lot of amorphous materials in there, there should be some big broad hump in your pattern anyway, so you should be able to know to try those. In any case, so it lists them in that order, and then also it has this other number here, log n. That's just the number of times that mineral appears, or a number of locations that mineral appears in the mineral evolution database. So there's something like 300,000 different locations where they have people reporting what minerals are there. And so I've color-coded the different lines in this table based on that number. So higher number of locations means a brighter color. So darker ones are more rare minerals, and the lighter colored ones are more common minerals. So that just can give you some insight about what might be more likely to be there. In any case, in this case, the number 1 and 2 things that show up are pyrophyllite and quartz. And then a few after the quartz there are just chert, which is just cryptocrystalline quartz. So let's focus on these first two here. I'm going to select pyrophyllite. It turns green, and the pattern shows up here. And it does look like there's peaks in some of the right places. Okay, but on the other hand, pyrophyllite isn't all that common, whereas quartz would be something I'd expect. And if you look at the quartz, so I clicked on quartz as well, and it has peaks in a lot of the same places, including the main peak. So I'm just going to deselect the pyrophyllite and go with quartz. So I'm going to say try selected here, click this button. And so I can have more than one thing selected here, but right now I just have one selected on this table. I'm going to say try selected, and it will add that on the optimization page to my selected table. So this is my list of ones that I've selected. And you can see it's added in quartz into the analysis, and some of these peaks are now accounted for by the quartz. All right, so now I'm just going to go back to the compare page, and you can see I have a new list in the suggested table. And the first one on the list is calcite, which would be extremely common. So I'm going to click on it, take a look, and yeah, it does appear that where I have calcite peaks, there's something there in my data. So I'm going to try selected, and it'll add calcite to the analysis. Okay, so I'm going to go back to compare again. I still have lots of peaks to fit. And now we're hitting something that's a little more complicated. So the first one that comes up is rectorite. So there's a couple rectorite in these top hits here. And then a couple illites. And then there's several smectites. Okay, so here's the problem. The most diagnostic peaks for a lot of these phyllosilicates like this are at low angles. But because some of them, like your smectites, can swell to varying degrees, some of those peaks are going to be quite variable. So just depending on what cations are in the interlayer, which are easily exchangeable. The peak can shift around. There's a lot of variation in the peak shape due to particle size effects and disorder, things like that. So it's hard to tell these things apart, right? So illite is a 2-to-1 phyllosilicate. Smectite, a 2-to-1 phyllosilicate. The illite doesn't swell, the smectite does. Rectorite is actually an regularly interstratified illite smectite combination. So it has, every other layer is an illite, and every other layer is a smectite type of thing. Okay, and you can see the rectorite would not be as common of a thing as your smectite or your illite. I'm going to look over here at low angles here and see this kind of broad hump right there in the pattern, in the blue. I'm sort of tracing out there. Well, that indicates to me that there's probably some smectite in here. So I'm just going to choose smectite first, okay, because it's pretty obvious to me what's going on there. So let's look at this sodium smectite, and you can see down here what kind of peaks it has. Maybe choose a couple of these calcium smectites, and you can see there's the difference in how this low angle peak moves around, just depending on whether there's sodium or calcium, and then it could be sharper peak or a broader peak depending on other factors like the particle size and so on. In any case, very similar patterns, all of these, especially in the analysis area, which is 19 degrees to 64.5 degrees. So I'm just going to, why not try all of them at once? Okay, so they all show up in here. Doesn't see, I mean, and I'm going to actually click on this smectite Wyoming calcium montmorillonite sample right here, or the standard, and make it go away. It was only picking up, about 1.5% compared to much larger percentages for these others. So let's leave these two different montmorillonites in there for now. And I'm going to go back to the compare page. All right, so now we have a bunch of feldspars. So potassium feldspars and plagioclases that are popping up. And this is another case where if I say click on this intermediate microcline and then this anorthoclase, they have a lot of the same peaks. Ordered microcline, orthoclase. Okay, so here's what I'm going to do. I'm going to pick these top ones. I'm just going to try them all again. And then maybe I'll get rid of all but a couple of them. So this orthoclase right here that has the lowest percentage picked up here. So I'm going to get rid of that. And then maybe I'll leave these other ones here. Let's see. Let's go back to the compare page. Now it wants a kaolinite, so that would be pretty common. Let's look at that. And I can see, oh, here's a peak right here and a peak right here that could be explained by having kaolinite there. So let's try that. go back to the compare page. It wants dolomite. Let's click on it. Notice how the dolomite, this cell right here that I'm hovering over, is selected already. I can't click on that. I have to click on another cell in the row in order to select the dolomite. And you can see here's the dolomite pattern, and once again it looks like there could be some there. Especially the major peaks seem to be showing up in our data. So I'm going to try that. So, okay, I'm going to go back to my compare. Now it wants a chlorite. That's magnesium chlorite here. Let me click on that. So notice this little peak right here. This is out of the analysis area, but there's a smaller, sharper peak. I suspect if you calculated the d-spacing, it would be around 14 angstroms. So that would explain this. Also, it would enhance this peak that kaolinite was, is fitting that, but we can add to it by adding some chlorite. And then there's this other peak right here, notice. And so it looks like chlorite might be a good candidate, so I'm going to try that. All right. So note that our raw total weight percent is actually getting up to near 100%. Our degree of fit is getting down toward 0.1, which is our general goal. Let's go to the compare page. There might still be some things to fit, though. So the two things that are coming up here are two pyroxenes, so two clinopyroxenes, augite and diopside. So diopside and augite are basically the same thing, but diopside would have somewhat more magnesium and augite would have somewhat more iron in it. So maybe we have some of that kind of thing, a clinopyroxene, in this sample, but since there's a solid solution between augite and diopside, the particular sample we have in there might actually be something that's in composition between the standard and the RockJock standard for augite and the RockJock standard for diopside. So why don't I select a couple of them right there? So I'm going to try them. Okay, and I look down here. Well, and so they're not too far apart, how much they're saying there is, so I'll just keep both of them in there. Now, I'm going to do my compare again. Now it's telling me chalcopyrite. Now that would be kind of odd in a sample like this, but what the heck, it's a synthetic mixture. It looks like chalcopyrite, the program is just kind of wanting it to use it to get a better fit on this peak here, but it's already fit pretty well. It's just, its shape is a little bit off. The next biggest peak for the chalcopyrite would be sort of broad thing around here. I don't really see that kind of thing, or this broad hump here. I don't see an indication of that. So since that would be odd to have chalcopyrite here, and I'm not really convinced I need it, maybe I'll leave it out. Here's a plagioclase. So this would be sort of giving a better fit to some of this complicated area where feldspars typically have peaks. So I'm going to try that. Okay. And oh, I'm sorry. Let me go back. I'm going to actually click on that anorthite. I think I accidentally clicked and deleted the ordered microcline, but I'll get to that in a minute. See, we have these feldspars here. This is our problem here. We have feldspars in there, and feldspars are hard to tell apart with powder X-ray diffraction. And plus there's solid solution going on. There's X solution, so one sample might have two different compositions, and so on. So I'm going to spend some more time on those. So why don't I go down here. I'm going to, on this list, alphabetical list of standards, and I'm just going to select a bunch of these alkali feldspars, and I'm going to select a bunch of these plagioclases, because they're just so hard to tell apart. But then I'm going to winnow them down, each down to a couple, I guess. All right, so I'm going to look at the plagioclases first, and look at which have the lowest raw weight percentage in the analysis. So it's this one, the oligoclase. So I'll click on it, get rid of that. Now I'll look and see what the new analysis says. This other oligoclase it wants me to get rid of. Now, okay, the lowest now is this labradorite. And then this andesine. And then anorthite. All right, so, and then let's do the feldspars, or the potassium feldspars. I'll get rid of sanidine, and then orthoclase, and orthoclase. Okay, so I have a couple potassium feldspars, and I have a couple plagioclases. All right, so let's look at this. I'm going to look at my fit. See, like I said, that over in the below the analysis area, some of the peaks for the clays are more variable, so we want to look there, especially for sharp peaks. Those tend to be less variable, but we want to make sure we have those covered. Are we missing any peaks? Not really. And overall we have a good fit. So my raw total weight percent is 101.2%. That's really good. And my degree of fit is 0.0916. So we're going for 0.1 or below if we can. All right, so now I'm going to record the results for this sample. And I'm going to look at sample 2. Now this is sample 1B2, so that's the first mixture, second replicate. And you can see that I'm getting really good results for that, 100.7% and 0.102. First sample and first mixture, third replicate, also looking good. And then the first mixture, fourth replicate, also quite good. Okay, so now let's move in. So the next four are sample 2B1. That's the second mixture, first replicate, and there's 4 replicates again. So I'm looking at the fit here, and you know, it's not There's something weird going on with the background right here. I'm not sure what, but in any case, the peaks seem to be accounted for, and raw total is 95%. That's not bad. And then less than 0.1 for the degree of fit. Let's make sure the other replicates of the same sample are similarly good. Oh, actually, I'm going to go back to sample 2. I'm going to start recording results every time I go to a new pattern. So it just transfers the same settings. I make sure those settings seem good. And then I'm going to record the results if I like them. Okay, the replicate 3 looks good. Replicate 4 looks good. Okay, so the third mixture, first replicate, looks quite a bit different, but it seems like we're still doing a good job picking up all the peaks. So these seem like reasonable settings for this series. Okay, so I'm going to record those results. Look at the other replicates. Record the results. Okay, now the fourth mixture. And once again, it is really looking good. So I'm going to record those results. Go through the other replicates and record them as well. So by doing this, we can actually get an idea of what, how variable your results will be based on just different samples of the same stuff. Not like you maybe prepare it slightly differently. The packing in your X-ray diffraction holder is slightly different. That can give some variation in results. And also there's going to be error just due to the nature of this kind of program, where aside from sample preparation issues, there's also issues with how close are the samples in the RockJock library to, or the standards in the library to the actual minerals that are in your samples that you're examining, because that can affect the shape and position of the peaks somewhat. Okay, so I'm going to go over to my results page, and it should have all this recorded. Now you'll notice that I have the ungrouped results. These are all normalized to 100%, and the grouped results. Now it's important to group your results because, for instance, remember how I said it's kind of hard to tell apart, especially if there's not that much of it, a lot of these feldspars. Well, if I said, oh, there's 8.98% of intermediate microcline in here, nobody would take that seriously because the technique is not good enough to tell it apart from other types of potassium feldspar or even plagioclase that well. Oh, but I can group them together and say, okay, there's about 13% potassium feldspar, about 9.5% plagioclase down here, and so on. Okay, so I'm going to quickly go over for this sample 1, that is our first mixture, and let's look at our results compared to what they're supposed to be. For calcite in this mixture, there's supposed to be 10%. And we got about 11%. So that's not too far off. For dolomite, there's supposed to be 5%. And we got about 5.6%. For clinopyroxenes, there's supposed to be diopside in here. So I had in both augite and diopside, but there's supposed to be 5% diopside. We got, let's see, that is 5.03% total clinopyroxene. Right? And remember, I told you those two minerals are in part of a solid solution series. So whatever diopside sample is in the mixture, it actually might be in composition something in between the augite and diopside samples that happen to be in the RockJock database. Okay, so we have quartz. It says there's 17.5%, but it turns out there is actually only 15%, so we're 2.5% off there. It's a little more significant, but still not bad. So K feldspars, we have almost 13% in the analysis, but in the mixture, it says there's 5% orthoclase, 5% microcline, and 5% some other kind of potassium feldspar. So 15% total. So we got about 13, and the actual is about 15% K feldspar. Plagioclase, we got about 9.5% plagioclase. It turns out we had that split between bitonite and albite. Actually, there was 5% each of labradorite and bitonite. So we were within about 0.5% of the total plagioclase, but misidentified one of the plagioclase. Like I said, especially when there's small weight percentages of things like plagioclases and K feldspars, it's hard for the X-ray diffraction to pick up the differences between them very well, even though it does a decent job of saying how much total plagioclase and how much total K feldspar there is. I have 1:1 phyllosilicate clays here, 15%. And that includes just kaolinite. And it turns out there is 15% kaolinite in this mixture. So we are only 0.25% off on that. For the 2:1 clays, that would include both the smectite and the chlorite. I include under that heading. Sometimes it's hard to tell apart the chlorite as well. But anyway, if we split them apart, we have about, about 19% smectite and 4% chlorite. In actuality, the mixture had 20% smectite as opposed to 19, and 5% chlorite as opposed to 4.1. Okay, so both of those really close. So, and you can look over here on sample 2. That's the second replicate. Sample 3 is the third replicate, and there is some variation in the numbers we get, even though they're just different runs of the, different splits of the same sample. For instance, this calcite, we have 11.16, 12.18, 10.71, 11.36. So they're pretty close, but there's some variation in the analysis. But doing something like this, you can get an idea of what kind of error you would get just from the sample preparation. Okay, so I'm going to go over now to the next few samples. Sample 5, that's sample 2B1, so that's my second mixture. So let's compare a little bit. There is supposed to be 15% calcite in here, and the program picked up right around 15% for all of these next four samples here. Okay, 14, 15%. For dolomite, there was supposed to be 7%. And guess what? Our analyses are around 7.5%. Okay. Let's see. For our clinopyroxenes, let's see. I have a total of 2.73. Okay. And there's supposed to be 3% diopside in the mixture. So pretty close. I'm getting 5 or 6% quartz for these analyses. And in this mixture, they're supposed to be 5%. For the K feldspars, looks like we're picking up around 6.5 to 7.5-ish%. And it turns out that for K feldspar, let's see, yeah, about 7.5% is what it's supposed to be. So pretty decent. So for our plagioclases, we got 5.75% here, 5.6, 5.9, so 5.5 to 6% or so. And it's supposed to have 5% total plagioclase. 1-to-1 clays, looks like we're getting around 25% for that, and indeed there was 25% kaolinite in the mixture. And let's see, there's supposed to be in the mixture 25% smectite, and we are picking up around 30% smectite. So anyway, we could go through and do the other two mixtures. It's similar accuracy, but that should give you an idea of what kind of accuracy you can reasonably expect with this kind of technique, and what kind of differences in accuracy you might get, or lack of precision you might get at least, just as a function of preparing different samples to put in your sample holder.